out here. Okay, so I'm just going to give you a little bit more of an overview of some of the science that Steve Siems and I plan to do in Stream 1. And if you look at my pictures that I have on this introductory slide, then you can see all of them have cloud in them. And that's because what I'm going to talk about concerns clouds mostly. So I'm going to focus on really two main objectives, which basically have two main themes. So one is understanding the atmospheric dynamics, which effectively covers many of the physical processes we have in our atmosphere, such as the global and regional circulation, convection and precipitation, and also on radiation. So the effect of changes in the atmosphere on the radiative flux at the surface and also at the top of the atmosphere, which is relevant at both the sort of short-term meteorological scales and also for longer-term climate. And to do this, we're going to use recent field observations and satellite observations to better understand the dynamical and microphysical, so small processes that deliver precipitation to the Antarctic continent. And we're going to observe and understand how the Antarctic climate has changed over the past 40 years. From existing data sets, but also we're going to improve on those data sets so that they're more fit for purpose and hopefully discover the underlying global circulation features that are causing the observed changes and use the findings and comparisons with models to help improve the future projections. And when I'm talking about the sort of global circulation features, by that I'm meaning some of these main causes of climate variability, which have already been touched on, such as El Nino, which is you're probably all very familiar with and is characterized by sort of unusually warm ocean surface temperatures in the equatorial Pacific. Or perhaps it could be the SAM, the Southern Annular Mode, which refers to this north-south movement of strong westerly winds with no particular seasonal pattern in the mid to high latitudes of the Southern Hemisphere. Okay, so to touch on the first one, so one of the key atmospheric processes is atmospheric rivers. These are a really important mechanism that connects the subtropics, where the air is warm and wet, to Antarctica. And you can see on the right an example of an atmospheric river. This one's mostly over Australia. And it's basically a sort of a high pressure blocking ridge which leads to a big flowing column of a huge amount of water. And when it moves inland, okay, so when it moves inland over regions such as Antarctica, it sweeps over the mountains, it cools and it creates really heavy precipitation. So these events, they're not that common. There are about 12 events per year in West Antarctica, for example, but they're associated with about 40% of the total summer meltwater over the Ross Ice Shelf, and this can be up to 100% of the precipitation at higher elevations. Okay, the second theme I talked about was the radiative effects. And these are sort of summarized in this diagram showing all the different feedback processes in the polar region involving the atmosphere, ocean, surface. So TOA here refers to the top of the atmosphere. We have shortwave solar radiation in yellow, long-wave infrared radiation in red, and a red plus sign means that you get positive warming feedback, and a negative blue sign corresponds to a negative feedback. And you're probably very familiar with some of the feedback, such as, you know, when ice and snow melts, it lowers the surface albedo, the surface becomes darker, which leads to an increase in absorption of solar radiation and amplified warming. Or how perhaps in a warming climate, the amount of water vapor in the atmosphere increases, and this amplifies the greenhouse effect and leads to further warming. You may be less familiar with some of the cloud feedbacks, and we have both signs for the cloud feedbacks because they can occur simultaneously. And whether it's a cooling effect or a warming effect, it really depends on the amount of cloud, the height, the thickness, the type of particles. Is it ice, is it liquid, or, you know, the time of year. So as an example, you could consider a scenario whereby you have decreased sea ice extent in winter months results in greater cloud cover and increased downwelling long-wave radiation, leading to further sea ice loss. So that would be a positive. Or another example is as the climate warms, the fraction of liquid cloud increases over ice clouds, and this results in the clouds having a higher albedo. They're more reflective, and this reduces the amount of shortwave radiation at the surface. So if you think that sounds pretty complicated, you will probably not be surprised to learn that it turns out that clouds are really one of the big unknown factors when scientists try to build computer models of climate, which brings me to my next slide. Okay, so this is an example from one of the climate models. This is from the UK HADGEM 1 model. It's quite similar to the Australian one. It's the latest result. It's quite a good model. And the variable I'm showing you is the outgoing shortwave radiation. And typically we evaluate models with observations. So what I'm showing here is actually the difference between the Ceres satellite, which was designed to accurately measure outgoing broadband radiation, and the model. So if the model and the observations agree, then it's white and we're all happy. And if you can see any color, red or blue, then that's not so great. That's when the models disagree. So if you focus in on this sort of shortwave anomaly here at Antarctica, you can see some of these values are going down to like -30 watts per meter squared. And that is actually a very large value in comparison with the total amount. And this is quite significant as it can lead to excessive heating of the ocean surface, sea surface temperature biases, and also subsequent problems with the atmospheric dynamics. And this slide shows why it's really important to model that region correctly. So this is results from a recent paper by Mark Zelinka, and he looks at the estimates of climate sensitivity of the model. So the climate sensitivity refers to the amount of global surface warming that will occur in response to a doubling of atmospheric CO2 concentrations. And there's a little sort of cartoon on the right here, which shows that you can basically break that down into the CO2 warming and the contribution from the feedback processes. So the results from this latest CMIP comparison, and this stands for Coupled Model Intercomparison Project. And it's a program by where modelling communities submit their models every few years for intercomparison and evaluation. And the HADGEM and the Australian Axis models are examples of these. So this slide's looking at low cloud feedbacks. So we have the cloud feedback on this axis here. We have the latitude along here. The cloud feedback is basically calculated by differencing the all sky radiation, so radiation at the top of the atmosphere with cloud and clear from just the clear. And you can see that the southern hemisphere is a really important area. So this is showing the results to a quadrupling of CO2. And the blue lines are showing the old model. The orange lines are showing the latest model. And if you just focus on the top plot, which is just showing you the total contribution, you can see that this has increased for the newer models. So the solid lines are showing where all the models are agreeing and the dashed lines where they're disagreeing. So there's still quite a lot of uncertainty in this estimate as well. Okay, but this is one of the main reasons why this climate sensitivity has increased in this new model comparison. Okay, so what are the key questions that we hope to address, these sort of big questions? So this is the current scenario. We have lots of mixed liquid ice cloud. It's very difficult to simulate, but it really affects the cloud reflectivity, the albedo, sunlight reaching the ocean surface, the cloud feedbacks on global climate and sea ice, and we have problems with boundary layer cloud as well. So we want to know what are the key cloud processes missing in the models that need to be identified and addressed. What is the influence of this complicated mix of clouds on the radiation budget, so the surface and the top of the atmosphere? Are we observing some changes over time, and how are they linked with this large-scale climate variability? And can we improve this representation in the models? So what's in our toolkit that will enable us to do this? Well, harsh conditions in the southern oceans make measurements really challenging, but there's been a lot of international interest in the last couple of years, and this has resulted in quite a few campaigns joint with Australia, in particular Steve Siems has been involved with some of these campaigns. And these campaigns have involved aircraft taking observations, ships taking lots of observations, measurements on the ground, satellite observations. And what the really nice thing is we've got this really nice data set where lots of measurements are made together, they're all co-located, and we can really extract a lot of information out of this data. There's also possibilities of other measurements, such as those made at arm stations, and the possibility of new measurements associated with measurements being made around the new runway. Okay. So that's the campaign information, but we also have satellite data, and we plan to exploit lots of multiple data sets, drawing on the strengths of each. So we have long time series and temporal and spatial coverage from the AVHR series of data, and this is something that I'm sort of been intimately involved with creating some of these data sets. And we want to improve them and sort of take away some of the sort of Northern Hemisphere bias that inevitably appears in them and make them better fit for purpose. And also some of the sort of more recent satellites that can give us a vertical profile, a really accurate profile through the clouds. And we'll combine these with all the ship and aircraft and the ground observations as well. And there's another couple of tools in our toolkit.
3 minutes, Caroline.
Yep. We have COSP, which is this observation simulator package, which we can use to perform comparisons of satellites and observations with models, and hopefully improve those models by improving some of the parameterizations. Okay, so just to summarize, Antarctic and Southern Ocean clouds need to correctly be represented in regional and global atmospheric models, and we need this to improve sort of the daily operational forecast as well as future global climate predictions. That's really one of our key aims. And we're going to use satellite observations and measurements for these campaigns to really evaluate and narrow these uncertainties in precipitation, cloud, radiation over the Southern Ocean and Antarctica. I'm really hoping that some of the results will feed into some other projects, and we're really happy to work with other people. And yeah, looking forward to working with SAEF. Thank you.